problem for today is minimum cost to make at least one valid path in a grid. This is a hard problem. We'll just start by looking at the problem first. Given a m into n grid, each cell of the grid has a sign pointing to the next cell you should visit. If you are currently in this cell, the sign of the grid can be down. You can say right, left, lower, and upper. Okay. I'll explain the example to you. We have to go from the start of the grid 0 0. The coordinates are 0 0 to the end of the grid here. We have to go till we have to go to the coordinate m minus 1 and m minus 1, which corresponds to this box of the grid. We can this you can and you can also see you can modify the sign on a cell with cost 1. You can modify the sign on a cell one time only. Return the minimum cost to make the grid have at least one valid path. This is the 2D grid problem, and the 2D mostly start explaining the problem. If you have to go from here till here, and the cost the arrow in this the first you can say box, the arrow points to the left. That means we have to basically the shortest path doesn't matter. The shortest path doesn't matter. For example, if we go from here, the shortest path would be to go from the left, right, and bottom. But this would need changing many arrows. For example, this would need changing many arrows. We have the shortest part. The shortest part in a grid doesn't matter, but what matters is we have to basically you can say at least the path needs to be valid, but it does not need to be the shortest path. The valid path does not have to be the shortest. That means the path may be the longest path, but you have to minimize the number of, you can say you have to minimize the number of arrows you have to turn. For example, I'll just explain here. Path does not need to be shortest. Minimize number of arrows change. This is the main problem. You will start at 0 0. Okay, the path to 3 3 this point is as follows: 0 0 to 0 1, 0 2, 0 3. Then we will change one arrow. The cost would become 1. We'll come here. This arrow would we have changed this arrow to point downwards. It'll come here. Then we'll come. Then we'll simply go with the flow. Left. Then there are no options for us to go. Then we have to change. Then we have to change this arrow to point downwards. This will come here. Then we'll go with the flow. Right, and then again we'll change this arrow to downwards to point downwards. This will reach 3 3 m into 3 3. We have changed one arrow here, and the last arrow here. So the total cost is 3. In this case, if we come here, left, right, we already have an arrow pointing downwards. So we need not to change this arrow. This will come here, right, left, then bottom. This right, left, and this here. We have already reached the last, you can say, index of the grid. Hence we need not there is no cost. So because all the arrows are pointing in the correct direction. Here, the last example, we start from here, we go to this point, but this arrow points to the you can say left to its left, but we can't go here, and so we have to change this arrow to point downwards, and this will reach the last in just one cost. We can solve this using BFS and BFS and Dijkstra. I'll just first solve the question using Dijkstra, then we'll optimize using BFS. This is a standard DFS algorithm, a standard Dijkstra algorithm. I'll just paste something I need. this is the basically the coordinates of the grid, m number of rows and number of columns. Valid function if just to check if the array is in bounds. The last is the directions array. Basically, yeah, this is the left 0 1 1 0, and basically this point is the four directions of the, you can say, our neighbors. If we are here, we can go either here, either here, either here, or here to point downwards. For Dijkstra, we need a priority queue. I'll just make a priority queue. I'll something like this. There will be three things. There will be three things stored in the priority queue. First is the cost. The starting cost would be 0. The starting index is starting column is 0. The starting row is also 0. To explain here, cost row column. We also need a, you can say, 2D distance array to basically not to only proceed. We need this for Dijkstra algorithm. This is the 2D distance array. I have initialized all the, you can say, indexes with float infinity. This is a very big value in terms of Python, and we have initialized the basic the starting as 0, because the starting we would be having a distance of 0. So we will now write a simply write a basic Dijkstra algorithm, something like this. While priority queue cost x y is equal to cost heap pop of the priority queue. This will get us the basically the you can say this is a min heap. So this will get us the minimum distance, because in Dijkstra we try to be greedy and go always with the smallest, you can say, cost, which is this one. We'll check if x is equal to m minus 1 and y is equal to n minus 1. We'll simply return the cost, because in Dijkstra whenever we find a path, it always is the shortest path to the specific node, because the first time we reach this node, it will minimize cost. Now the main thing lies here. For example, there will be two scenarios. I'll just write here cost 1 and cost 0. If we want to go here, for example, to go the right, and the arrow also points the same direction, then there will not be any cost. But if you want to go here and the arrow points to the right, then we need to change this arrow to point downwards. Then the cost will be +1. I'll just do x dash directions direction cost. I have tried to make this function modular. So I'll just make a new function here. I'll pass in x, y, and the type would be x into y. There are 4 types. We have right, left, lower, or you can say upper. I'll just initialize this function here. X, y, and type. If type 1, the one if the one type is, you can say, right, the right type. The one is the right type. Hence, we'll just return a tuple x and y plus 1. Just copy paste this. the type is 2, 3 and 4. The second type means left, hence this would become minus. The type 3 becomes lower. The row, the x coordinate is increased by 1. The y remains same, and in case of upper, this would give us this. This function would return us the coordinate. This function would return us the new coordinates that are current grids arrow points to. Now for dx dy in directions, new row new column is equal to dx plus x dy plus y. If not valid, that means if it is out of bounds, then becomes continue. Then this continue. Okay, and for the next thing is updated cost. We have to calculate basically calculate a new cost. Updated cost is equal to cost if a new row is equal to x dash and new column is equal to else cost plus 1. This is simply the main thing being done here is, if for example we want to go, if for example if we want to go here, and if we want to go here, and the same arrow also we want to go to right, and arrow also point to the right, then there will be no cost. The previous cost would be initialized this, for example this. But if you want to go downwards, but the arrow points to the right, then we need to change this arrow to point downwards. Then this would take extra cost, which I'm doing here. Then we simply need to, you can say, update if this new row new column there is nothing new being done here. This is basically the simple Dijkstra algorithm. The new thing only is this, to basically recognize that there will be no cost if you are going to the same direction as the arrow is pointing to. Otherwise, previous cost plus 1. Nothing special. E push PQ NR NC distance NR NC something like this. If we do not find anything, this would never be the case, but I'm just in case. Okay. I'll just try to run this. Okay, it seems to be working fine. I'll just try to submit it. It's being submitted quite fine, you can see. But we will now optimize this solution to use BFS instead of Dijkstra. The complexity for Dijkstra is E log V, but the complexity for Dijkstra is E log V. Because we are using a heap, this function and this function take log n time. Hence, we will the complexity for Dijkstra is basically the simple Dijkstra algorithm is E log V. But we will try to optimize this using. We will try to do this using something called B01 BFS, which is being described here. It is a quite you can say advanced algorithm, not used quite in interviews, I think so, but this algorithm is basically used if the weight of the edge is either 0 or 1, which is in our case, because the cost is either 0 or 1. 0 1 in case, so if the direction of the arrow is same, then previous cost, otherwise previous cost plus 1. Hence there are only two types of weight, 1 or 0 weight. We'll try to implement this. First we need to basically make this something like a Q. I'll remove this. I'll also make this a DQ. I'll just make this DQ. Q dot pop left. Same. This is a simple. This is a simple, you say, BFS algorithm. I'll just tell you. You can see. I'll explain the new thing I've done here. Okay. Something like this. This would work fine. Okay. If that means if the direction of our arrow the direction of our going and the direction of the arrow are same, then for example then you need to append the new node to the left of the queue, because the BFS always takes the BFX uses a queue, and the queue pops from the front. So you need to append the smaller way to the front of the queue, like explained here. Yes, we can simply use a normal queue and append new vertices at the beginning if the corresponding edge has weight 0. Otherwise, weight has 1. If the weight is 0, we have to append to the front of the queue, or else we have to append to the last of the queue. I'll do something like this. A queue dot append left. I need this. I also need this. Okay. Because this cost and this cost remains same, or else if the arrow and r direction are same and a cost is less than the already you can say already reached cost, then you need to append to the front of the queue. Else if cost plus 1 is less than you can say our previously otherwise previous distance, otherwise there is no point there is no point exploring this option, because this will give us you can say a larger distance than before. So hence this, I just remove this append left. This append left basically append to the front of the queue. This appends to the right. You can say bottom of the queue. This should work fine. As you can see, the complexity is quite better. The complexity for this algorithm is the complexity for Dijkstra is E log B, but complexity for BFS is number of edges. You can say number of edges.